Okay, so in this video, I will be covering the subroutine instructions now, and this is the last instructions that we're going to cover. Okay, so subroutine instructions, here are the main commands that we'll be covering. Actually, we're going to be covering a couple of them, but I'll talk about a few of them before we do that. So the first two are call and rcall. So before I get started with all the instructions, the subroutines are, you can think about them as C programming. In C programming, you use functions. So subroutines are basically, you can think about them as functions, something that will deviate from your main program, do something, and come back to your main program. So the way you actually call that main program is by saying call, and then you call that main program. I'll show you a few examples in a few minutes, but I just want to explain how things are working under the hood, and then we go to an example to explain everything. Okay, so the instructions that I care about is if you want to call the subroutine, you just basically say call, and you provide that N here is the address of where the subroutine is. Basically the label, kind of like what we did with goto and the unconditional branch. So our call it's called relative call. It's also going to call the subroutine, but it's relative. The difference between these two are very similar to the difference between goto and the unconditional branch BRA. This one here takes a full address, which is 21 bits, so it will need a couple of words in the program memory to be stored, as opposed to the rcall, which takes a relative address. Basically, it takes well, I'm here, go jump like negative 200 program instructions before the current location or after it or whatnot. So basically, this is only 10 bits, and you can fit them. I think they are 11 bits because we're talking signed integers. Okay, so they're 11 bits, so you can actually jump 1023 addresses after in the positive direction or in the negative direction 1024. Okay, so well, frankly speaking, I generally use call. I don't usually use relative calls. I think the only, like, in my thinking, the only place where you want to use an R call is if you're short in program memory or you're tight on program memory because your program is so big. I haven't bumped into that situation yet. Okay, two of them actually takes a couple of cycles to implement. So in terms of cycles, you're not going to be saving anything, and none of them actually affect the status. Now, after you call the subroutine, you're going to jump to it, you're going to do your own thing, and then you're going to have to return. And the instruction to return, you have a few of them as well. So one of them is actually a return, and that's the one we're going to be using today. And its purpose is just to go back to wherever we were in the main program. Okay? There's a couple of other returns. There's a return LW, which pretty much puts a specific number or literal in the working register and return. So whenever you return, you're going to see that the working register has that particular value into it. So this is something to keep in mind. We're going to be talking about what the S is doing shortly as well, and it's related to what happens to the working register. I'll just explain it with an example. It's much easier. So this one here, we're not going to bump into it today, but we're going to be dealing with it later. This is return from interrupt enabled. So an interrupt is something we're going to be talking about later. And it's just something that you're doing your own thing in your program or your program doing its own thing. There's a way to interrupt that program from an external factor to the microcontroller, maybe a sensor, maybe something that you need to take care of right now or urgently. So you stop your program, you go do that thing, and then you return. It's very similar to calling a function, but you're not calling it from your program. Something external to the microcontroller is calling it, and this is how you return usually. You return from the interrupt. Okay, there's a couple of other options which are, or other instructions, which are the pop and push. We have seen them. I'll review them shortly, but they basically allow you to push and pop into the stack. Okay, so stack, we have talked about the stack. Let me just do a very quick reminder about what the stack is. So the microcontroller we're dealing with, which is the 4321, does have something we call a hardware stack. This hardware stack is here. If you look at this diagram, we have 31 level stack, and we have a stack pointer. We have talked about it at the beginning of the course, but I'll just repeat these for convenience now because they're very relevant now. Okay, so we have 31 locations in the stack. So, okay, so what's a stack? Well, a stack is just basically a place where you can store program memory into it. So let me give you an example of what's going to happen. So we have seen that we wrote some sort of a program. We are in program memory, and the program counter is pointing to the next instruction to be executed, and now this is the one that will be executed. So you're running your own thing in your program memory, and all of a sudden you jumped into a location here, and that location is 14. That tells you, you know what, you need to call some sort of a function, and that function is here. So calling that function, meaning you're going to change the program counter to actually reflect this here. So we're going to have to change it. But before we do, let's store what is the location I need to return to after I'm done running my function or subroutine. Okay, so I'm currently here. I'm about to evaluate that jump or that call. I'm going to call that function in here. But in order for me to know where to return to, what is the value of the program counter, what's the next instruction to implement after I'm done with the subroutine, I need to store it. So we're going to store it in the stack. So the stack stores it, and then I do my own jump, and I jump to that subroutine. That function actually execute 1, 2, 3, and let's assume that here is I'm done, and I issue the return. Okay, so the return takes that value from the stack, pops it, and puts it in the program counter, and my program continues. Okay, so what I want you to see is the following. So I'm going to repeat this here because it's relevant now. Now, what's happening here in this particular instruction, I am calling that function. So calling that function in here, or that subroutine, let me call it a subroutine. So whenever I call that subroutine, what I'm effectively doing is I'm pushing a new value, which is the value 16, into the stack. Okay, and the stack can, again, the stack here in the microcontroller can hold up to 31 of these. Okay, so we have 31. The stack, again, is a register that basically has 21 bits with the length of each word is 21 bit because it should store a program counter value, which is an address, program address memory, which is 21 bits, so it stores all of them. And I have 31 rows of them, and I have a stack pointer that points to where I am in it. Okay, so again, we call, it pushes it to the stack, and then you go and you do your own thing, and then when you want to come back, you pop it. Okay, so these push and pop, you don't necessarily need to do them when you're doing a call and a return. The call technically pushes and jumps, and the return pops and jumps back. Okay, we're gonna see these shortly in an exercise or an example. Okay, so again, we continue our program, and that's it. So the two instructions or that microcontroller allows us to is pushing and popping. So I'm going to talk about push and pop very briefly. So here's my stack pointer, and the stack pointer is currently pointing to this particular location, and that particular location is what we call the top of the stack because it is the last value that you entered into the stack, and my stack pointer is pointing to it and it's telling me this is what you pushed last. Okay, and now let's assume that I have a new value I want to push into the stack, and that value coming from the program counter. So what I can do is after I issue a push command in here, you're going to see that value will be stored in 0, 5, and the stack pointer is going to actually advance one location forward. Okay, so it advances one location forward, and that's where my stack is. Now all the previous values are available to me to access. However, usually in that microcontroller that we have, you can only read and write the last value in the stack, or what we call the top of the stack, or TOS. There's a special function register called TOS, and it's split into 3 registers because you need to save every byte separately. Okay, but let's call it now top of stack, and you can get access to that, and you can read that value if you wanted to. Okay, so if I want to push another value, you push it, and then you can see that the stack pointer just advances 1. We have covered this previously. I'm just going back forward, just a quick reminder before I actually just go ahead and solve an exercise so that you can figure out what is actually happening when we write a program. So the pop is opposite to push. So what you're doing is I have the top of the stack here. I can read it, but let's assume that I want to really come back to that location that I stored because I'm doing something. My program counter is in a different location. So popping technically takes that value here on the top of the stack, puts it in the program counter. So the program counter comes back to that location and continues the program from there. Now what's happening is the stack pointer is pointing to the previous one, making the location 06 in this case available. It doesn't remove what's in the stack here, but it just makes it available, which means that if you issue any push now, you're going to overwrite it. Okay, and you can issue another pop, you can issue another pop, you can push as many pops as you want until you reach the 00. If you reach the 00, that location in our microcontroller, it's an indication that you don't have anything in the stack, that you're currently sort of in either reset or in the main program. It has its own applications. It has several applications like the stack, and there are a couple of flags in that stack pointer. So that stack pointer, because it's only pointing to 32 places, it only needs 5 bits to store 32 places, or because 31 and the 00 does not count, so 32. So what do I do with the last 3 bits in it? It turns out to be that the last 2 bits are flags to tell me whether my stack is full or my stack is under full, because I'm trying to pop something but I don't have anything in it. Okay, well, I'm not going to go to the details of how to use that stack. You do have manual control over it. And what I did is I'm going to post on Blackboard an application note. Application notes are usually the manufacturers, in addition to the data sheet and all the information, they post application notes to teach you how to use certain things. So I found this application note which manipulates the stack of this PIC 18, and it talks about what do you do with the stack and how do you actually push. So these are the top of the stack. I told you there are 3 registers. It's top of stack, upper, high, and low, very similar to the other 3-byte registers we've seen. We've seen this habit before, and then we have the stack pointer, and it tells you, well, you can do this and that. You can, like, if you're interested, you can read through it. So the push and pop instructions that we have, I'm going to scroll all the way back here. Okay, so the push and pop are not generally found in all microcontroller. This one is allowing us to do it because it's allowing us to do some manual manipulation of stack. I don't think you're gonna need, at least not in this course, you're not gonna need any push or pop. You're not gonna need to use them. And the thing I can think about, like, that you would need to use them is this application note tells you can do program direction, holding data, and passing. You can read it. The one I think about is the creating software return stack. Let's assume that you really need to jump over 31 places. So the hardware stack doesn't allow you to jump more. So what you need to do is you need to go to data memory and create your own software stack, and you need to actually make them connected somehow. So this application note refers to it very briefly. It doesn't mention how to implement it, but I'm pretty sure if you look for it, you're going to find it. So these two instructions, the push and pop, allows you to utilize software implemented stack on the data memory, okay, and connect it to the hardware stack that we have, so that you can actually expand it to over 31. We will not need it. We're not gonna use it. The 2 instructions we're gonna be using today is call and return. Okay, so why don't I just now we know how things are working. Why don't I just go to the example? So we're gonna do this example in here. Okay, so let me just do that. And here, okay. So here's this example, and in this example, what I'm trying to do is write a program to compute the square of a number. Okay, we have done something similar before. It's basically I'm gonna multiply a number by itself. Okay, but what I want to do is I wanted the calculation to be in a subroutine so that we can see what things are doing. And the reason why is because we're going to see in 4, what I'm going to do is I'm going to call that subroutine in a couple of times. I'm going to provide a number, I'm going to square it, figure out what that square of that number is, and I'm going to do it again. Previously, what we had to do is copy and paste that code several times. Kind of like how we learned functions in C. Okay, they taught you, hopefully this is how they taught it to you, is like you shouldn't be copying and pasting code, you should be reusing code. So subroutines allows us to employ code reuse. Okay, but anyway, we're gonna go through it. We're gonna go through the first 3 first, and then we'll go to the 4. Okay, so the one telling me, okay, implement that function in a subroutine, and it's telling me where the original number should be stored, let's say at location 50, and where the answer should be. And the answer, because I'm multiplying an 8-bit number by an 8-bit number, I need 16 bits, so I'm going to store them in 51 and 52. Okay, so let's get started with that. So okay, so here's that code. Let's do that. Okay, so we're gonna do first. This is part of code, so we're gonna put it in a psect. We're gonna call it code, and now I'm gonna say, all right, here's the start of my program, so that I can, after a reset, I can jump right here, and I'll figure out what to do with it. But because I don't want to remember this x and x squared and where they're stored, so what I'm gonna do is I'm just gonna give them names, so my code is a little bit more readable, and I don't have to scroll back and forth between the slides and my code. Okay, so I will call this x, and I'm gonna call it equal to 0x50, and I'm gonna call it x squared, for example, low, and I'm gonna make it equal to 0x51, and here I'm gonna do x2 high, and I'm gonna make it equal 0x52. Okay, so now I can refer to x squared low and x squared high. This will store the low byte, this will store the high byte of that multiplication. Okay, so the start. Okay, so we're gonna come back to the start. The start is gonna call the subroutine. Let's implement the subroutine itself first. So what I'm gonna do is I'm gonna implement the subroutine, and I'm gonna say, okay, what I really want to do. Why don't I write the program and then I'll call it. So what I really want to do is I want to multiply a number by itself, and that number is x. So the first thing I'm going to do is I'm going to move f, okay, from x, and I'm going to put it in the working register, and I'm dealing with access bank, okay. All right. Then what I'm going to do is I'm going to multiply w and f. Basically, I'm going to multiply the working register with the value stored in the register x. Effectively, I'm multiplying x by itself. I moved it to the working register, and then the next instruction is telling me multiply the working register, the content of the working register, by whatever is stored in x. Well, that effectively will compute x and x. Okay, and now what I'm gonna do is I know that if you guys remember, it's here actually. So if I go back in here, you can see the ALU has the ALU has a multiplier, and oh, come on. Okay, let me just. Okay, so the ALU has a multiplier, and that multiplier is here. Let me just show you. So that multiplier here, it actually stores the result in product high and product low because it's 16-bit. These are two special function registers. So I'm going to utilize these two functions in here. So, okay, so what I'm going to do now is I'm going to store these two values, the answer of the production, the product from moveFF. I'm going to take the low value product L into the x2L, and I'm going to move FF, and I'm going to take the high byte, and I'm going to store it in x2 high. So this is what I would effectively do, okay? So of course I'm going to have to store something in X and test that functionality. This is what we have done before. So if I want to test that function and figure out whether it's working or not, what I need to do is I'm going to say, well, I'm going to move the literal W, and I'm going to, let's say, I'm going to put 5 in the working register, and I'm going to have to move WF, and I'm going to move it into, let's say, X, and the final answer is going to be in the file register in A, and then I'm going to call everything here, and that here will result in the 5 squared. I'm going to see that product, basically, I'm going to see 25 in these two locations, x2L and x2 high. But this isn't what I want to do, because what if I want to do now 10? Not only 5, but 10. I'm going to have to copy this code, and I'm going to do the same exact thing if I want to see the 5 and the 10, okay? So what I'm going to do is I'm going to put this in a subroutine, and it's as simple as saying, okay, let's give it a name, and let's say that name is SQR. Okay, and now this is a subroutine. Okay, so this is a subroutine, and calling it is as effective as just jumping from the main program, which is in start in here, which I could just easily call main, and I'm gonna go to the square, and I'm gonna come back. So, but any subroutine has to return, so you're gonna have to use the command return. Okay, so we're gonna return in here. Okay. So this is the subroutine. So what I effectively done is I basically did number one in here, 1, 2, 3. Okay, so 1, 2, 3 tells me the calculation should be done in a subroutine, and x should be stored at location 50 and x squared. So I have x squared and everything. Now what I want to do is I call it a couple of times. So let's start with calling it one time, and then we'll figure out how to call it the second time. So how do I call a function? Well, it's as simple as saying, okay, I'm going to move and let's say LW, and I'm gonna put 5 in here. This is the one I wanted to see. So what I'm gonna do is I'm gonna move it WF into X. Okay. So I'm gonna move it into X. That's correct. So I'm gonna move it into X. So what I did is I put it in the working register. I put a 5, and then I moved that 5 and I put it in an X. And now instead of just figuring out this function and move it, basically doing the same, I'm doing the same thing in here. Not the same actually, because this actually moved the content of X into the working register. But anyway, I'm rambling here a little bit. So what we need to do is we need to move from this main program. I want to go in here to the subroutine, and the subroutine is expecting to see some sort of a number in X, which I already have because I moved it. It's gonna do the square of it, and it's gonna store it in a couple of locations. So when I return, after whatever I'm gonna put in here, when I return, I should get that number squared in these two locations. So, and it's as simple as saying call SQR. And SQR, just, you can name it whatever it is, it's a label. Okay? So what call and return, these are the two new instructions you're seeing today. So what call does, it does the following. Okay, whenever your main program is running, it sees a call, it says, okay, you're trying to go to a subroutine. Let me see what is the program counter here. I'm gonna store it so that I know that I need to come back in here afterwards. Okay, so I need to come back here to whatever like I wrote in here. So I'm gonna go do my own things, and the return would actually just come back in here. So I'm gonna show you what's happening in the stack because of whatever I did right here. Okay. So that's pretty much what we need to do, and my program is done here. I can do something else in here. I can do whatever I wanted, okay? Let's see, for example, let me call, well, I don't need to call anything, so let's say just stop, and I'm gonna say branch stop, okay? That's the program. Let's just see it running in its most basic form, okay? So we're gonna do that. We want to debug, okay? So the debug worked. Okay, that's perfect. Okay, so I'm gonna pause it, I'm gonna reset, and I'm gonna show you what's happening in here. Okay, so what I need to do is, like, you can see that the program memory is here. I want to add something new now. So I'm gonna go to window, and I'm gonna go to target memory view, and then I'm gonna see the hardware stack so I can see what's inside that stack. So I'm gonna click on it. So generally speaking, you should see nothing in here. So my stack pointer is here. This is where my stack pointer is actually at location 00, which I told you that means I don't have anything in that stack. This is stored because I paused the debug, so it probably ran. Yeah, it did run, and it's basically in here. The result that I'm expecting to see is here. But anyway, let me just do this here. I'm gonna fill that memory with a bunch of zeros. So basically I zeroed out everything. Let's get started. So technically when you start, you're gonna have a bunch of zeros in here and a bunch of zeros in the stack. But my stack pointer is at the very beginning. So let's jump in here. So we're gonna see that I'm jumping in the move LW. Let me just expand this. I am technically moving into the working register. I'm moving a 5. So this is my 5. And now I'm gonna store it in wherever X is. I don't remember where X is. It's 50. Okay, so that location 50, it should be here. That should move the number 5 in there. Okay, so it moved it. That's exactly what I would expected to see. And what I want you to see is the following now. So here's what's new. Okay, so call, this is a new instruction. And again, it's a couple of words because it's not R call. This is 2 words. This is why you have a NOP at the very end, because I need a couple of places to actually store it. Okay, so what is it calling? Well, the call turns out to be that it actually computes similar to branch and the other thing. It computes where I'm supposed to jump to. So it computed some address. Okay, what is that address? 1FF2. Okay, 1FF2 is this particular one here, which is move 50 to W, which is that. It actually computed the address of square. Okay, so whenever I called square, it effectively computed the address in here and it jumped into it. But I know maybe my main program actually have a bunch of things in here, like a NOP and a NOP and a NOP and a NOP, or just like anything, like no operations. You might be doing something else with that X squared, which we will do shortly. Okay, so what happens is I need to know where to return to, because look at the program counter. The program counter is currently pointing in here, FEC, which is the call. Whenever I'm actually gonna implement that, okay, whenever I'm gonna click step into it, it's gonna go jump directly to the square. It's gonna do its own thing. So my program counter has changed, and if I want to continue my program, I need to figure out where to return to. So what you're gonna see is the value that will be pushed to the stack is the next instruction location, which is that here, 1FF0. This is what you see here. Technically it should have been empty, but because it ran before, because I didn't pause it. But anyway, you're gonna see my stack pointer is here, indicating that all these locations are free. So whenever I'm gonna jump through, you're gonna see my pointer, my program counter actually jumped directly to wherever square is returned. And you can see my stack pointer now points into a location that is 1FF0. So that 1FF0 is here. This is where I'm supposed to come back to, which technically speaking is the next instruction. So what I stored is the next instruction after call so that I can come back to it. Okay? And that's what is happening. Now I'm doing my own thing. My subroutine here actually goes and copies that value, which is 5, and it copies it to the working register and multiplies it. This is something I think we've seen before. So it's multiplying it, and now I'm moving into the product high and product low. Okay, move FF product. It's like this should be product low. I think it's a typo, but anyway. I wrote it right, so it should effectively be okay. And I got the number. Look at this. This is return. Okay. So this is interesting. So it counted everything and it pointed out. And I think 19, if I'm not mistaken, 19 in hex is 19 hex is 25, which is 5 squared. This is what we should expect, and that's the correct answer. Okay, so that's it. So I need to return now. Now I'm here, I'm at this location, which is return. So what return does, it effectively goes to the stack pointer and tells it, hey, stack pointer, you see that value? Put it back in the program counter so that I know where to return to in my main program. So if I'm effectively doing this, you're gonna see that that will be popped out of the stack, put in the program counter, and my stack pointer is gonna point to the level, the lower level of the stack, which is 0, 0 in this case. So we're gonna do that, okay? And you're gonna see that's exactly what happened. So you see that my program counter now is pointing to the next instruction, which is just a bunch of branch. Okay, so that's how subroutines generally work. Okay, so what is the case where I use these 31 locations? I'm gonna show it to you in an example, but basically if your subroutine is calling another subroutine and calling another subroutine is calling another subroutine, you're basically stacking them. And one example of a stack, or something that I usually remember what a stack is. A stack, I think about it as a stack of trays. Whenever you go to a food court or something, you have a stack of trays. Usually you have access to the tray on the top. You shouldn't be, well, some of us actually take the tray from the middle of the stack, but generally speaking, you're supposed to take the stack from the tray from the very top of the stack, and the last one you put is the first one you get out. It's pretty much the same thing in here. You think about these locations as trays, okay? Okay, so this is what happens. Now, what I want to do is I want to explain a little bit. There's part of the instruction I didn't explain at all, and that basically is here. Let me zoom out a little bit so that I can scroll faster. Okay, so that part of the instruction is what we call an S. Okay, by default it's a 0, this S here, and this S in here. And you can see in my program here, what happens whenever I called, that S happened to be 0 because I didn't specify it. So the default is 0, and that S here, the return here happened to be 0. So what does that mean? Well, let's see how let me show you what it means. Okay, so let me show you what's happening. Let's assume that okay, we put 5 in the working register, and when we came back, the working register had 5. So let me do this. So I'm gonna put 5 in the working register. I'm gonna move it to the X. Okay, and now what I'm gonna do is I'm gonna clear the working register. Okay, I'm gonna clear it. So I'm gonna store 5, and I want you to monitor what's happening to that working register. Okay, so let me just do that one more time. I'm gonna debug. Okay. All right, so we debug. I'm gonna pause it, reset. Okay, I'm gonna fill the memory with a bunch of zeros. Okay, so I zeroed out everything. Frankly speaking, nothing is gonna change in the stack pointer. It's somewhere. Okay, hardware stack. There you go. Nothing is gonna be different here. But let me just do that. All right. So we jump. Okay, and my working register will have a 5. We'll move it to wherever X is, and now I'm gonna clear it. So my working register is 5. Okay. So now it's gonna be 0 because I cleared it. Okay, and now I jump. Okay, so we jump to whatever the routine is. It's storing the same exact stack pointer. Nothing's different in here. And now we click, 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 and now it's telling me, okay, it's time to come back. Okay, this is what the return is. Look at the value of the working register now, because what's happening inside the subroutine, I actually moved the value of X, which I happen to be 5 in this case. I moved it into working register. Okay, and now multiplied it. I'm done with it, but my working register now has the value 5. Remember, before the jump, what we did is we cleared that working register. So after the jump, what do you think that the working register would have? Well, I'm returned. Now I'm in the main program, and my working register has changed. So I want you to see it here. Let's take a look at the code. So what happened is I called clear. So my working register happened to be 0. I called, I came back, and my working register had a different value. So this might be a problem. Okay, so sometimes, like, it depends on what you're trying to do. Sometimes you are trying to come back to change the working register, or maybe your working register was where you're going to do all the changes or all the calculation in your subroutines. Sometimes you really don't want it. It's not the only register that is changing. Actually, you're going to see that actually the status register has changed as well, and the bank select register, which we are not using. It's the one that allows me to use the different banks in the memory, but these 3 registers will be changed. So in order for me to store, okay, before the jump, if I wanted to come back and I want my working register to stay exactly where I left it, what you need to do is you need to set that S flag into 1. So what 1 does it does the following. It actually goes and figure out what is the working register value is, which is 0 now. I'm going to push it to something we call a shadow. Okay, a shadow register, or S working register, shadow working register. And it's going to push the same thing for the status register. It's going to do the same thing for the bank select register, the BSR. So it's going to push all these 3 registers into shadow registers in the CPU. Frankly speaking, I tried to look for them in the SFRs and I couldn't find them anywhere. But they exist. They're called shadow registers, okay? So these this now, if I'm putting that 1, of course I need to do it also with the return, because I want in the return to tell it, hey, move the values from the shadow registers back. Okay, from the shadow register. So take the value that you stored before you jump and put it back in whatever the working register have. So now the difference between these 2 programs now is the following. I just added the 1, of course, after clearing. You're going to see that after I'm going to go through this, I'm going to reset. I want you to see now my working register has a 5. I'm going to clear it. And I'm going to go through the call. So the call is going to jump down. It's going to put 5 in the working register. It's going to do its own thing by multiplying. And then whenever I'm returning, look at the working register here. Whenever I return, it got back the values that was in the working register originally. So before the call, my working register was a 0. After the call, my working register did not change. So that's the purpose of this little 1 in here. Okay, so sometimes it's useful if you don't want the value of the working register to change and your subroutine have to use it. I mean, in this particular microcontroller, I mean, the working register is the main register that we use to do all the calculations. We need to use it. So if you need the older value, it pushes it there. Okay. Good. So I don't think I'm done with the example. Let's see. So the last part of the example, it's probably asking me to call that function a couple of times. Okay. So, all right, let's do that here. So call that subroutine 2 times with X. What I'm effectively going to show you is what's happening here. Okay. So there you go. So I called it with the 5. And now what I'm going to do is I'm going to move into the working register. I'm going to move the value, let's say 10. I want 5 squared and 10 squared. I'm going to move it to whatever X's should be. And now I'm going to call SQR, and I'm going to call it with a 1 so the working register would not change. So what you're going to see, I want you to see the hardware stack in here. Let's do that. Okay, I need to debug it. Okay, we're going to pause. And I want you to see what's happening. So what's happening here is after the reset, I'm going to jump. I'm going to put the 5. I'm going to just zoom through it very quickly. It's computed the 5 squared now. So now here's the deal. So of course, I just want you to see one thing. Whenever I did call, it now jumps to 1FF2. Well, 1FF2 is here. I think it's a different address if I remember correctly, because I have more instructions here. Just using that label SQR, the assembler figured out where their new address is, so I don't have to worry about, oh, I'm calling this particular address. Just call the label, it's easier. Okay, anyhow, we continue in here. You're going to see that I am now back. The working register is 0 because I cleared it before. In here, I'm going to put a 10. I'm going to put that 10 in the X location, which is here, the 50. Okay, and I'm going to do that. And I want you to see what's happening to the stack pointer now. The stack pointer, okay, I'm going to do before the call. Here's where I'm calling the function again. It's the same address I'm calling, okay? But now my location 50, which has X, has a different value. So I'm computing a different number. Okay, so you're going to see that the call is jumping to the same exact location, where is my subroutine. But my stack pointer, however, it's a little bit different now. So my stack pointer is now at 0. It was pointing to, but because I returned, this value still exists again. Even though I popped it from the stack, it still exists, but its location is available, so I can override it. So previously it jumped back to 1FE8. So 1FE8 was here. It's actually the move 10. This is basically where it jumped back to. I want you to see what's happening now. It's taking the call. It's telling me I'm going to store the next instruction, which should be stored in location 1FF0. So whenever I click call, you're going to see that 1FF0 got pushed into that stack, so that I know I need to return here. Okay? And it's going to do its own thing. It's going to multiply and it's going to return, and you can see that the working register is at 10, and now the new value, which is, I think this is 100, because 10 squared is 100 in hex. Okay, you can see it, that it's here. Now, of course, if I was able to fit it in just 1 byte, but if I needed 2 bytes, I'm going to see them in location 01 and 02. Like, let's assume I put, I don't know, maybe 100, and you figure it. You realize this. It's like you can test it. Okay, so key takeaways here is the call does the following. It's actually doing a couple of things. I'm going to write them manually in here. What it's doing is it's actually pushing the next program counter value, and then it's going to the location SQR. That's what it's effectively doing. Whenever you do a call, it pushes the program counter into the stack pointer, into the stack, sorry. So stack pointer moves forwards, saves that value, and it jumps. And the return is on the opposite side. The return, what's it actually doing, it's actually pulling, okay, from the stack and putting it into the PC, the program counter. That's what it's doing, okay. And then it's going to whatever the PC is, whatever the program counter is jumping back basically to the location I'm interested in. These are the two things it's doing. You don't have to do this go to and push and pull. They're already embedded in the return and the call. And that's what I was trying to say. So these instruction push and pull, push and pop, sorry, not pull. If I wrote pull, please change it to pop. They're just so that you can manually do these things. What you really need to know is the call and the return and that flag in here, whether you want the working register to change or not, or return to its own values before. Okay, so now I think that concludes this particular example. So let's see the other example, which is here. Okay, another example, let's do that. So this example here, I want to write a program to compute the sum of squares. Okay, you see I'm building on the program that I just did. So the calculation of each x squared should be done in a subroutine. This is what we just did. But what I'm saying is I'm going to have not only one x, I'm going to have, let's say, 4 or 5 or whatever it is. I think I set the example to 5. Okay, we're going to sum the sum of the square of 5 of these x's. And every time I need an x squared, I shouldn't be copying and pasting this code 5 times. I should just call that function to do it, or that subroutine. Okay, and then I'm gonna utilize another subroutine to compute the sum of the two 16-bit numbers. Remember, every single time you do an x squared, you're gonna get a 16-bit number. If I'm interested in sum of squares, I need to sum the 16-bit and another 16-bit and another 16-bit. I'm just gonna put it in a subroutine. And now, lastly, what I'm gonna do is I'm gonna assume that I have 5 numbers, so my n is 5. And I'll go from location, for example, I think 50 to 54. I shouldn't go to 55. That's a typo. Okay, because that makes it 6 location, not 5. Okay, 0 to 5 is 6 location. Anyway, it's from 50 to, let's say, 54. And I'm going to use the memory fill to fill these memory location with the sequential. I'm going to just right click and fill it with, so for the test. And the sum should be stored at these 2 locations. All right. So I'll just put it on the side. Maybe I'll refer to it if I need to. All right. So let's see what I need to do. So I will type a few of these equals. And so let me just do the square. I think should be the same. The main program is going to change a little bit, so I'm going to keep it. So what I'm going to do is I'm going to pause a little bit. I'm going to write a few of these equal signs so that I don't so that we can refer to it. It's much easier than remembering whether to store the x somewhere or whatnot. So let me just pause. Okay, so what I did here is I wrote a few of these equals so that I basically named some sort of location in memory so that I would refer to it. It's much easier to explain to you instead of telling you like, oh, I'm storing in location 50 or something. So let me explain to you what are these. So n is number 5. I need just to store how many numbers am I doing the sum of square for, and the answer here is n. Okay, so or not the answer, I called it just n, and I'm gonna store it in location 0 0. You don't have, like, I just wanted to. Okay, I'm gonna store the number 5 in it eventually. Okay, and now here I'm gonna say, well, okay, so I have a bunch of numbers in here, so I'm dealing with some sort of a table or an array, or you can call it a table or an array. Okay, and I'm just gonna store the first number is gonna be at 50. Okay, at 0x50, and this is basically the pointer. You're gonna see that we're gonna, again, if you're dealing with a bunch of numbers or a range of numbers or an array, we probably are using FSRs, the file select register, and that will be stored in FSR0. That will be the point, it will be pointing to that location. And now finally, I did y, and the y is actually just, the y is an answer. And of course the answer, since I'm summing 16-bit numbers, I need a low byte and a high byte, so I decided to store them in 60 and 61. And I basically have a bunch of numbers that I need to square. I'm going to put the number to be squared in location 70, and its square is going to be saved in 71 and 72. So you can see I basically did not change my subroutine, and because I did these equal, even though I changed the x and the x2l and whatnot, nothing changed here. It will write them to the right location. Okay, that makes my code a little bit more readable if you're doing these equal signs. Okay, so what am I asked to do? Well, I'm asked to do the square in a subroutine. It's already ready for me. I like that. Now what I need to do is I just need to know that I will be summing a couple of 16-bit numbers. It's very similar to the lab you did or you're doing this week. I think the deadline is today to do it, but anyway, today is Thursday. Okay, so, well, anyway, what we need to do is we need to create some sort of another subroutine, and that subroutine should sum a couple of 16-bit numbers. That's how I want to think about it. I'm not going to worry about how and whatnot, like what's happening in the main program. Now I'm going to say, I'm going to call it sum16, okay, because it's summing 16-bit numbers, and I'm going to tell you, okay, what am I summing? Well, I am summing whatever previous value is stored in the y's. Okay, my answer, let me think that the y is accumulating these numbers, the final answer, into whatever is stored in x2l and x2 high. So frankly speaking, what you're really doing is I'm going to move the wf from x to l, basically the low byte of the x. I'm going to move it to the working register, and now I'm going to add to it wf, okay, yl, and I'm going to store the value back into that yl, and I'm going to put it there. Now, this is something to think about. Whenever you're doing your lab, or we did this similar example before, we used the add wf, and we assumed that there's no carry coming in. However, now because I'm accumulating in the y, so this sum of 16, what I want to do is maybe I sum the first two numbers, like let's say 1 and 5, and I got the number 6 and the carry was 0. But what if I'm summing 10 and 10 and I got the number 20, so it's going to be 0, and there's some sort of a carry coming to the next location. So because I'm accumulating these in the y, I'm going to actually use the w with the carry. So I'm going to worry about that carry. Okay, and I'll have to repeat the same exact thing I did in here, and that basically I'm going to move wf, but this time for the high byte, okay, and I'm going to add wfc, and it's going to be y high, f, and a. And now after I'm done with this, I'm going to return, and I'm going to assume that I really want to keep all the working register and everything as is. Okay, so I'm going to return with a 1. So I created these two. Again, I am summing the first low byte, okay, and I'm going to take whatever carry in here. I'm going to sum the high byte, and I'm including the carry that got generated now, or like from the low byte. And in the low byte, I'm taking a carry that is coming from the previous numbers I summed, okay, from the previous numbers I summed. So now I have the square and I have the sum. Okay, so I implemented the sum of squares, I implemented the squares, and I implemented the functionality of the sum itself. So what I need to do right now is I need to go to my main program and call them to implement some sort of a sum of squares for 5 numbers. Okay, so let's do that. So what I'm going to do is I'm going to tell you, all right, I know that I have 5 numbers, so this is basically where I'm going to put the n, okay? I'm going to move this into n, move wf, I'm going to put it in n, so my n, which is location, you don't need to remember if it's location 0, 0, now has the value 5. I know that I'm going to iterate. I'm going to use it in a loop, as you probably can anticipate. I'm going to use it in a loop to loop over 5 times over the locations that are going to be through the the FSR0, FSR1 for that matter. Okay, I'm gonna clear the whatever answer I have. Okay, remember I'm accumulating these numbers in y, so I have, if I'm summing, I'm accumulating like you did in programming. You have to clear that variable or that location you're summing into for the first time, just so that you have 0 plus 1 plus 2 plus whatever it is. Okay, and then I'm gonna clear f, y, h, and then a. Okay. And now what I want to do as well is, because for the first, and it's like, who knows what's happening, what I want to do is I want to clear that carry bit here in the status register. So what I'm going to do is I'm going to say bit clear f, and I'm going to go to the status. I'm going to tell it, hey, you want to clear a certain bit in status register, and that bit is bit 0. Okay, and I'm using access RAM to do that. Okay, so that instruction here goes to the status register and zeroes out bit clear, or clears out. It is 0 bit, which is the carry bit here. Okay, all right. And now what I need to do is I have almost everything ready. I think I just need to load the FSR 0 with whatever table. So you see, this is why this is convenient, because my table, I'm assuming that my numbers start from 50. So okay, so it goes through. Now what I have to do is just implement that loop. So I'm gonna call that loop. I know that a loop is coming. Okay, and what am I looping? Well, what I'm really doing is I'm doing the following. So I'm pointing, FSR0 is pointing to the first, we're going to see different numbers in here. It's pointing to 50, which is basically my first number to be squared. So I'm going to move it to wherever x should be. Okay, so let's move that. Okay, so I'm gonna move that. I'm gonna move from FF from INDF0, which is basically where my FSR is 0 pointing to, into location X. However, I know that there's another, because I'm looping, I know that my pointer is pointing now to the 50. I should point next instruction to 51. So instead of INDF0, what I'm going to do is I'm going to do post increment 0. Okay. I am basically moving the content of location 50 to whatever X should be, because I'm going to call that function square. Okay. So I'm going to call that square now, and call, and I'm going to do square, and I'm going to say 1. So I don't change the status register or anything else. Okay, now I know that my x squared and x squared is stored in a certain location. All I have to do is just accumulating in the y, and I know accumulating them, meaning I need to basically just call the sum 16, and I'm gonna call that with 1. Okay, so again, what I'm doing in here is I'm moving from whatever the FSR 0 is pointing to, I'm moving it to X, then I'm going to call the square. And square, all it's doing is taking whatever you put in X, it squares it and puts it in a certain location, X squared and 1 out. And then I'm calling the sum 16, and the sum 16 is doing, it's taking whatever you stored in X2L, which just happened to be, because the square wrote into these two locations, it's actually the X squared low byte and X squared high byte. And it's just accumulating them in the y, and that's pretty much it. I think if I repeat this enough times, I should get my answer. So the way I want to do it is by decrementing f, and I'm going to decrement n. I'm going to store the value in a, and f actually in n back in n, and I'm going to say branch if not 0 into loop. Okay, and that's pretty much it. So this one here is supposedly, it's supposed to do everything I'm supposed to. Okay, so now this loop should be done, and I think at the very end of the program I'm gonna have locations where are my YL. So location 60 and 61 should have those values. So let's build this. Okay, and you can see, okay, so I'm paused, I'm gonna reset. Okay, so what I'm gonna do is I'm gonna go in here, I'm gonna do the fill memory, and I decided to go from I think 050 all the way to 0, let's say 54, I think 054, and I'm just gonna make it sequence. Okay, start, and I'm filling these locations that I'm about to sum by 0 1 2 3 4 as test numbers. You can fill it with whatever you want. I just filled it. This is number 0 1 2 3 4. Hold on. Yeah, 1 2 3 4 5. Yeah, it's 5 locations. Okay, good. So let's get started. Let's do that. We jump into my main program. My main program is moving the number 5 into n, which is at 0 in here. Okay, we did get that, and then I'm moving. I'm clearing the y, whatever 71 and 70 should be. I'm clearing them so that I can accumulate things in them. And if it is cleared at this point, but if for some reason or another it wasn't, my status register clear flag will be cleared, and now FSR 0 would be loaded with some sort of location to point to that 50, which is the very beginning of my table. And now I'm actually gonna start doing my loop. Okay, so I'm in the loop here. I'm gonna move that value. I'm gonna put it in the x location, which is location 70. So you can see that this one here, I didn't even have to write to read it. I can read that it's location 70 here. The assembler just translated these numbers for me. So in location 70, it moved to 0. Well, yeah. Okay, it moved to 0. It's gonna. Then after the 0, okay, after the 0, it actually jumped in here because I called I did the, after the 0, where am I? Okay. Yeah, after the 0, I called that SQR, okay? So it's actually just doing that multiplying. So basically it's computing 0 squared, and then it's returning them. And 0 squared is contained in location 71 and 70, okay, which are the years. 0 squared is 0, and now I'm summing, okay? Good, so you get the idea. Now I'm doing the sum, I return, and in the return you're gonna see, where is it? So in the return you're gonna see that I am right here now after I returned. After I squared the 0, after I summed it to the y, which was 0, so 0 plus 0 is 0. So you can see location 70 and 71, which are actually 60 and 61, which contain the final number is now 0 because I summed 0 squared. So I'm decrementing f, that here I'm decrementing n by 1, okay, because I'm iterating over 4 locations. We're going to do this, and now we jump. Is it 0? No. So we jump and do the same exact thing with the 1. Now here is where I want you to pay attention. So if you blacked out a little bit or not following a little bit, there's actually an error in this here, and I put it intentionally. So let me show you where this error is. Okay, so now my FSR0 is pointing to 1. Okay, so my FSR0 is pointing to 1. That's fine. I'm gonna do 1 squared, and then I'm gonna sum it. But I want you to see what's happening to the flag in here. Look at the flag. You see it? How did that flag happen to be C? Well, let's figure it out. I didn't do any carry. Like, all I did is I summed a bunch of zeros and whatnot. I didn't. So how did the carry and the digit carry actually became high in the status flag? Okay, again, so far we are stopping here. Look, we're about to square number 1. So we are right here now. Okay, I'm about to move it so that I can square it and sum it. But at this point, my carry from summing a couple of zeros is 0. Well, it turned out to be that this particular instruction here, which is decrement n, what it did the following. It actually went to n, which happened to be 5, okay, and it did -1 to it. And it turns out to be that this here, using 2's complement, okay, it generates a carry. So I want you at home to just basically go, you have an 8-bit 5, which basically equals 1, 2, 3, 4, 1, 1, 1, 1, and then you have 8-bit -1, okay, which technically is the same as saying the following. It's 1, 1, 1, 1, 1, 1, 1, 1, okay, and if you sum these two, you're effectively doing 5 minus 1. This is the 2's complement of 1. You can see if you sum these two ones, you're going to have a carry. So it turns out to be that this little thing here, it's going to mess up my calculation, and you're not going to get the correct number because my carry flag here. Remember, we're adding that carry flag. So if I square that 1, I'm going to get 1 squared, which is 1. If I'm summing it, what's doing here, it's going to take the carry, and the carry is going to be 1, and it's going to add 1 to 1, and I'm going to get 2. Let me show you. So look here, it's summed it, and now I want you to see location 70, location 60 is where the final answer should be, right? Location 60, yes. Location 60, look, I will get a 2 after that sum. Okay. After the sum, you're gonna see a 2. You see that 2? That's an error. How come a 1 squared, which is 1 plus 0, is a 2? So it turns out to be that this little carry with the decrement f happened to be problematic. So let me show you. Okay, so what I wanted to show you here is the data sheet. So I went to the data sheet, and I wanted to see that I used this particular instruction, which is decrement f. It decremented f. It exactly did the same, but the flags it actually affects all the flags. So, but I'm using that flag in my calculation. I don't want it to affect the carry, and even doing the 1s and 0s and whatnot, it didn't help much because what's happening in here is this decrement is not a call. I can't use that 1. Like, the 1 is basically you call, you come back, and everything stays the same. This is not a call. This is an instruction that changed my carry, and I'm using my carry in my calculation. So I need to look up for a different decrement that actually does not affect it. And if you actually go through the instructions, we have seen one, and this one is actually from the test. It's somewhere here. Let me just see it. It was actually right under it. So okay, so I looked for it. It's actually another decrement. So this decrement with the test. Remember, we had like some extra tests that we can you can test, review the test and skip instructions. So we have one of the skip and test instructions. Actually, it decrements f and skips of 0, skips of not 0, and you look at the flags, it doesn't affect these flags. So instead of using a normal decrement, we're gonna decrement f basically and do some skipping. So the solution was as simple as saying, okay, instead of using that, let us use the decrement f, okay, and then we skip f0, okay, and instead of using that here, so I'm gonna decrement that n. So I'm going to move 5 to -1 becomes a 4. Okay, I'm going to store that. And now if that number is 0, basically I reach 0. So I went 5, 4, 3, 2. If that number is 0, I'm going to skip that instruction. So that instruction should be, the ones that I'm not skipping should be branch actually. I should always branch to it. So if it skips it, basically you're telling it, hey, go to whatever you want to do afterwards. And I will do this here. Okay, while this is doing, all I want you to know is basically I'm using a decrement, but this decrement here did not affect the status flag. It's not going to affect it, so it's not going to affect my calculation. And you can see I'll reset, I'll go in here and I'll do that. I'll do that very quickly here. I'm doing the 0 squared. Okay, and I'm summing the 0 squared right now, and now here coming back, I'm decrementing. Look, my n has a 5. I'm gonna decrement right now, and I did not change the status flag. Okay, so now I can do my 1 squared. It's now did my 1 squared. It's gonna return from my 1 squared. Now I have 1 squared saved, and now I can actually go and sum that 1 squared back. And because my carry here, let's just see. Oh well, yes, I forgot to fill these numbers. I was like, where's the 1? Well, I forgot to. You're gonna have, because after the reset, I had to fill this with a bunch of zeros and ones. So you get the idea. You try it at home, and you're gonna see that I will do it. So I'm gonna pause and come back as if I filled this. Okay, so after that, you're gonna see that that number would have been actually correct in here. So you're gonna see that I'm returning. Now I'm gonna decrement from 4. If I do decrement here, I'm gonna get a 3, and you can see that the final number here is 1. And if you continue to work to the end, you're gonna see that you're gonna get the right number, which is, if you think about it, it's 1 plus 2 is 3, 3 plus 3 is 6, and 6 plus 4 is 10, and we got a 1e. Oh, these are hexadecimal. Oh yeah, I made that mistake yesterday. I'm not summing 1 plus 2 plus 3 plus 4. I'm actually summing 1 squared plus 2 squared plus 3 squared plus 4 squared. And if you sum them in hex, you're going to see that. You're going to get that number correctly. It's 1 squared plus 2 squared, which is 4, so that we have a 5 and the 5, and then I have a 9. 9 and 5 is 14, 14, and this should be something else, like 16, but 16 in hex, which is 10 actually, and you're going to see that it's a 1e. Try it at home. You'll see that you're going to get the correct number. Okay. All right, so now we move to the last example. Let me just close that. We're going to move to the last example, and the last example actually relates to the 7-segment program that we've done. So what this tells me is I'm going to move the 7-segment pattern from program memory, review the table RD, then moving tables and moving data from program memory to data memory. Frankly speaking, I'm going to copy that example and come back and modify it. But what we're doing, I'm just going to read the instructions and then we copy and we go and code it. I need to write a subroutine that translate and convert the working register value from BCD to the 7-segment. This is what we did, but now what I'm going to do is I'm going to move it into a subroutine by itself. And then after that subroutine, what I'm going to do is I'm going to write another subroutine that converts from an ASCII digit to BCD digit. Okay, so this one here from BCD to 7-segment. So you provide these 4 bits and you're going to display it in the 7-segment. This one here is ASCII, and as most of you know, ASCII has a bunch of numbers like 8, 65, and decimal and whatnot. But what I really care about is how they look. It turns out to be that the digits. I don't care about the A's and the B's. I care about digits. So in terms of digits, it turns out to be that their hex, okay, their ASCII hex. So for digit 0, its ASCII hex is 30, 31. You get to see the lower 4 bits, okay, are pretty much what I care about. So I'm going to write a function just to extract it. And ASCII, let's assume that you connected the microcontroller to some sort of a keyboard that generates ASCII. It doesn't generate BCD, it generates ASCII, and it's generating the ASCII for 1, the ASCII for 2, the ASCII for 3, and whatnot. So I'm going to move it from ASCII, I'm going to move it into its BCD, okay, and then from BCD, the last one is going to tell me from BCD, go and generate from, basically I want ASCII to BCD and then BCD to 7-segment. So technically I want you to, let's say, connect a keyboard to your microcontroller, and the keyboard is generating these 30, 31, 32, and I want you to end up just showing me the correct 7-segment pattern. Okay, and we're going to write them into subroutines, and we're going to call them from each other. Okay, the purpose of this exercise is to show you how a subroutine can call another subroutine. So let me get started. All right, so I went ahead and then copied the table. This is exactly the program that we've done. I just copied the one that we moved from program memory to data memory and whatnot. I just copied it in here, and I just want to go through that example, just the code very quickly. So this is the pattern, the 7-segment pattern that I'm going to store in program memory. Okay, these are how I'm gonna do that. Let me just see. Okay, so here's what I'm gonna do in my main program. I defined the 7-segment, where the 7-segment location. Okay, the pattern, the table where I want to store it in program in data memory. So I'm gonna store it starting from location 41 all the way through, and this is some sort of a counter so that I can move 0, 1, 2, 3 through it. The whole instructions in here, all they do, you can review them. I didn't change anything. All they do is they're going to move this 81 CF, blah, 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 all the way. They're going to start from 41, 42, 43 in data memory. So at the very end of here, I'm going to have my 7-segment pattern exactly where I want it to. And now what the problem is asking me to do is the following. So what the problem is asking me to do is, okay, write a few subroutines. The first one should move from BCD to 7-segment. Basically, this is what we're doing here. We're moving BCD and we're doing 7-segment. Okay, what I'm asking you to do is just please put this in a subroutine by itself, and that's what we're gonna do. Okay, so we do the subroutine here. Okay, let's call that subroutine, for example, what should I call it? Okay, we can call it, for example, BCD to 7-segment. Okay, all right, so we're gonna do that. And okay, so well, this is the main program, so I'm gonna move that back in here so that it is part of the main program again. Okay, so here's that. Of course, I'm gonna have to do a few things in here. Okay, so BCD to 7-segment. Okay, what do I want the BCD to 7-segment? It's gonna be very similar, it's not the same. I'm gonna assume that the value is already in the working register. The one that I want to convert is already in the working register, so I don't need to move a special thing into the working register. Okay, so here I'm going to assume that for this function, I'm going to assume that the working register has a BCD, and this function is going to return and change that working register and make it the 7-segment pattern. And I'm going to do the same thing we did before. LSFR 0, I am going to make it point to the origin, whatever that original table in the data memory is, and I'm going to move it so that it points to exactly that pattern I care about. Remember, again, I'm going to copy this into some data memory, and now what I'm asking it, hey, FSR, point to the location memory where it points to this, and then add to it whatever number BCD you have in the working register. Let's assume it's a 3, so this is 0 plus 3 is 3, so 0, 1, 2, 3, so FSR will point to the location that stores this value, and it will return this value. And I want it to return, okay, I want it to return. And my value is already stored in the working register, so frankly speaking, I want it to be changing the working register because this is where I want. I don't want the working register to be pushed to shadow and come back. After I call this, I want the working register to contain the correct value. This is how I want to run it. Okay, so this is the BCD to 7-segment. Okay, I think the other instructions I have in here is, okay, so you need another function that converts an ASCII digit to a BCD. Okay, so let's create another function that does ASCII to BCD. Okay, and let's see, how can I do ASCII to BCD? It's, well, let's do that. Well, ASCII is 31, 30, 30, 31, 32, 30, all the way to 39. To BCD, all you have to do is just keep the lower 4 bits. Frankly speaking, I can think about an AND with a mask, okay, 0F mask maybe. Okay, so all you need to do is, okay, well, your working register, you will assume that my working register already have that value, and it turns out to be that there's an instruction that I can actually AND the working register with a certain literal, and that literal is going to be 0F. Okay, so I'm going to assume that my value that I'm interested in the working register, and I'm going to AND it with 0F, and this is the literal, and it's going to store back. So it's going to change the working register by killing the most significant 4 bits, and that's okay for me because the most significant 4 bits, which are 3, I don't care about them. So I want it basically to move 30 to 0, 31 to 1, 32 to 1. All I'm doing is I'm killing the four most significant bit here. These again are in hex. Okay, so we do that, and I think that is pretty much the function. I don't need to do anything else. I just want to make sure that it is changing the working register, so I'm going to do return 0. So these are the 2 functionalities. So the last part of the problem, it's asking me to do what? Okay, the last part of the problem, it's asking me write a subroutine that converts ASCII directly to 7-segment. So ASCII not to BCD but to 7-segment. Of course I can write a subroutine to do this, but well, why don't I write a subroutine to do this? Okay, let's do that. I need ASCII to 7-segment, and frankly speaking, that subroutine should be doing the same, or should be doing the following. I'm gonna do ASCII to BCD, okay, and I'm gonna actually call it. It's a function. I'm just gonna call it, and I'm gonna tell it, hey, change the working register, change all the registers. I need you to change them. And then afterwards, I know from ASCII, I have my working register will have the BCD. Now I'm gonna call the BCD, and I'm gonna say to 7 segment, and my working register will have that value. And now here I can return 0. So what I've effectively done, you can think about it and see, is that I called I created a function here, I created a function here, I created the third function that calls these two functions. The reason why I wrote it this way is because I want to show you in what's happening in the stack shortly. Okay, you're going to see that the stack pointer is jumping a couple location, and the return hardware return stack, it's going to store a couple locations. All right, now we come back to my main program. Again, all it's doing here is moving from program memory to data memory. I'm not doing anything specific here. So now I'm going to test that program, and the way I'm going to test it is by saying, okay, let's say test the program. Okay, let's say I will move into the working register. I'm going to move the value. This is ASCII. Okay, this is ASCII 9 basically. Remember 39 is ASCII 9. Okay. And all I want to do is I want to change the working register value from that ASCII value into the 7 segment that represent 9. So I'm going to have call ASCII to 7 segment. And I'm going to do 0 because I want it to change the working register. So I'm going to call it with a 0. I don't want the working register to be pushed to shadow and come back. Okay, so we're going to do this here. Okay, to compile it correctly. Okay, we do that, we reset. Okay, so we're gonna jump in here, and what's effectively doing is, remember, all of these are data. Okay, all of these are program memory, but we are in program memory here. But what it's gonna do is gonna copy them here, and you can see it because it ran already. It copied them. I'll pause until I get basically to this particular location here. Okay. All right, so I'm pretty much here actually. So I stopped right here. So you can see I moved from data memory, I moved to 81 CF. So these are the data here. They became at 41, 42, 43, all the way through. And now what I did is I put into the working register the ASCII 39, which represent the number 9. Okay, and now look what I'm doing. I'm calling the ASCII to 7 segments. So effectively, I want the working register to change from 39. Well, what is the 9? I think well, it should be that portion here, which should be basically it should change to 84. Okay, and that's what I expect to see as a final answer. Okay, let's see what's actually happening. So here's my hardware stack. Okay, my stack pointer is pointing to 0, 0 because I haven't called anything. I am in the main program. Okay, and you can see that I am now calling some sort of a function. What function am I calling? The function stored at F1FF6. So 1FF6 is this guy here, which frankly speaking, it is that, which is the ASCII to 7 segment. Okay, so I'm gonna go in here. It did that, and you can see that 1FF6, its content is basically call and another call and then return. That's what it's doing. Okay, so what is that doing? But first, I want you to see. You see what's happening to the stack? Stack has 1FE8. Where's 1FE8? You can see that 1FE8 is here. Okay, 1FE8 is here. This is basically after the call. This is like the branch. So it's telling me whenever you want to return, you should return to this particular location because this is after the call. So I push the next location, which is what it's expected. But wait a minute, I'm doing another call in here. So what's happening in the stack? Look, so we're going to do this here. Because I did another call, so that call happened to push another value into the stack. Okay, what did I call? I called ASCII to BCD, which is right here. Okay, so I jumped back up. So you can see that I was down somewhere and then I jumped back up. But the return address that I'm currently at is 1FFA, which is right here, 1FFA. 1FFA actually points to this. So it's telling me, okay, you're going to call this, you're going to go do your own thing, and the next instruction you should return to is that. That's before you actually go back to the main. So you see the point of this stack, it's actually pushing these values. Now I have a couple of values in it because I have a couple of calls. One from the main to the ASCII 7 segment, and then one from the 7 segment to the ASCII to the BCD. So I'm currently here. So the stack pointer helps me just keep track of these, where should I return to? And every single time you do a pop, it's changing the program counter to actually change that or implement that. All right, so it's gonna do that. All it's doing is basically taking that and basically getting rid of the 3. That's the purpose of that subroutine. it got rid of it, and basically we have a 9 now, and now it's returning. So that return will pop that value and put it in the program counter so that the program counter comes back from the ASCII to BCD back to the ASCII to 7 segment. Okay, so here it is. So I'm exactly where I'm supposed to be. It's calling the other function now. And what does the other function do? Well, it's another call. So what do I have to do? I have to push the next address, which is the 1FFE, into that stack in here. So look what's going to happen. I'm going to go on call, and it did push that F1FFE, which is my return address in here. Again, my return to main program is still in the stack. I didn't call it. Okay, I didn't reach it yet. I pushed another one because there's another stack. So I'm here. I call this BCD to 7 segment. All it's going to do is going to manipulate the FSR, kind of like what we did before. Okay, and now it's going to change that working register from 9 to the value I'm expected to see, which is that 84. Hopefully, did I get the 84 here? Yes, it's that 84 that I'm looking for. And now it's going to return. Okay, so return meaning, okay, your stack pointer is pointing here. So basically, I am now here. I returned from here to here. Okay, and as you can see, the assembler is actually computing all these addresses for me. I don't have to worry about it because I'm using these labels. Okay, now that I am at another return, what does that return do? Well, it's going to pop that value 1FE8, put it in the program counter, and make the program jump back. So what is 1FE8? Well, 1FE8 is hopefully that stop condition here. Okay, 1FE8, which is here, which is the branch to 1FE8, which is correct. So we're going to do that. And what I wanted to see is, frankly speaking, the working register has the value I wanted to. So I started, so here's my program. My program here now, it's a lot easier to see. You see, like you don't even have to worry that there are all sorts of functionalities in here. All I want you to see is in here, you have moved some sort of a ASCII value to the working register, and then you called ASCII to 7 segment, and now that working register value has changed. Again, it's changed because I'm calling these functions with zeros, so that they do change the carry bit and everything else. Okay, so this is what I wanted you to know about the stacks and the call function. To recap, I really just covered one thing. Well, we have something called a call, and we have another return, and they take another flag, which is 0 or 1, and that is just to preserve the values of the working register, status register, or the bank select register, which we're not using. Okay, now we're ready to solve this week's lab.